Okay, hi everyone. So this is the practice questions for quantum physics. What we're looking at first is Quantum Physics Paper 1. Now you can find this on the website of Save My Exams, but they will not usually include the mark schemes. You will have to pay a fee for that. But you can also find these exact same papers in Physics and Math Tutor. I'll add the link as well for that again to remind you. But the only difference between why I'm not using the Physics and Math Tutor and I placed this one instead is because Save My Exams included this front page for each of the test papers, which gives you the time allowed. Here it gives you the total score, so out of 50, and then you can change it into a percentage, and then find which grades you are within depending on the percentage that you have achieved. You will also be recording this on an Excel file that I have attached as well to keep track of everything. You'll find them all clearly labeled, so please keep up with it. I would suggest that while I'm going through the answers, you do pause the video while you're answering the questions, see how well you would have done. Try and time it, so it's about 60 minutes. So this is the first example, but in the other papers, obviously, you should be timing them to get a clear, routine of what you're doing wrong, a clear routine of your time, because most of the people struggle with time. They feel like they have not enough time in the exams. So I'm going to begin with this paper. Start with, push it the other way, sorry about that. So now this is the first question. My trick in general is I see questions as a mystery, right? So you need to solve the mystery, that's what a question is. And obviously if you have a mystery to solve, like any normal detectives will do, they will look for clues. In this case, our mystery is the question, so what do we need to solve in the question? And within the question you have a lot of clues, and that's what you need to keep your eyes out for. What clues, what is linked to what I know already. So let's begin with question 1. Question 1 has about 4 marks for a long answer as well. Shows calculations. There's more parts of it as well later on. So let's start with reading it. What am I looking for? What are the clues? As I'm going through it and reading it, I will be labeling clues. I will be making the connections before I even start answering the question. That's the whole trick, to save you time. So we have, in an experiment, it is observed that when blue light, so this is an experiment, it's observed when blue light, blue light is shown on a clean metal surface. So we already are looking, obviously we know that these are quantum questions, but in an exam when you have to answer questions for a lot of different topics, you would not know straight away that this is a quantum question. But you see already that you have blue light shown on a metal surface and electrons are emitted. Now light is EM wave, is shown on a metal surface, which makes electrons be emitted. But with red light, there is no electron emission. Now we know that blue and red light are both part of the EM spectrum. Before I continue to the questions, our MIVX G, and visible light has red and blue on the other end. We know that the highest wavelength is on this end and the lowest wavelength on this end. That makes red so remember red and radio are quite close to each other. That's the way I use it to remember it. So red is closer to the radio waves, which means it has a higher wavelength than blue light, or a lower frequency than blue light, since C is equal to frequency times wavelength, as we know that c is the speed of light, which is a constant number, and since red light has a higher wavelength, it means it should have a lower frequency to match that. So state the name of the effect observed in this experiment. So what effect is observed? We have two effects that we should remember in terms of how electrons can get removed so far. One of them is the thermionic emission, and the other one is the photoelectric effect. So you have photons of blue light emitting electrons from the metal surface. And if you notice, it's also, since we call it the photoelectric effect, the question hints it in the name by saying the effect observed. Then we have describe Einstein's theory to explain. So you need to describe it to explain these observations. In your answer, you should include technical terms. Many of you ignore these parts, so please make sure you don't. To explain how the physics of quantum behavior, so even here it gives you further hint, it goes on to remind you that it is quantum behavior, so you should be focusing on the quantum physics, is used to explain the observations. Now, the observations are already mentioned in this part. You have blue light that emits electrons from the surface, but red light does not. So why is this happening? So how can you explain it using technical terms? Now, if you go on to the Word document that I have also attached, you should have a whole list of definitions, a whole list of proofs and experiments. In those definitions are the technical terms that you will find. So in this case, as soon as I see technical terms, I need to know that it involves quantum physics, so it will be photons. And since we're talking about the metal surface, I know that threshold frequency is another answer, another key term, technical term, and even work function. I also know that in terms of photons and electrons, there is a one-to-one interaction. Those are the key points to remember. So as soon as I see something like that, I need to be able to focus my answer on it. But I need to base my answer on what the question already is talking about. Not just general terms, not just, oh, it should have the height. No, it needs to be very specific to the question that you're being asked to gain full marks. So I can start by saying that, for example, only photons with a frequency above threshold frequency can emit photons, or whatever way you phrase it. You can be absorbed electrons, sorry. You can say, for example, only photons with frequency above threshold frequency can emit photoelectrons, or you can go on to say that only photons with energy above the work function will cause photoelectron emission. This is a very key point, and you should mention it. So if the photons is not mentioned, or threshold frequency, and even frequency and wavelength mentioned in this question, you might not receive the full marks. I will talk about what the mark scheme says as well specifically. Now we know that only photons with threshold with frequency above threshold can emit photoelectrons. Red light has a lower frequency than blue. Now, has frequency matter? Why does frequency matter? We know that since energy of a photon is equal to the Planck's constant times the frequency of the photon, then that means that blue light that has a higher frequency has more energy photon. So that means that red photons do not have enough energy, or the energy is below work function. Remember the Greek letter phi. And I already mentioned so far 2 points. I talked about threshold frequency, work function, and this is also one-to-one interaction, so you can't have red light photons, so you can't have 2 red light photons building up enough energy to get rid of 1 electron. So it is a one-to-one interaction. It is a 1-to-1 interaction, meaning 1 photon for 1 electron. I need to mention here that we included 2 points here. So the red light has a lower frequency than blue. It's 1 point, and since energy is directly proportional to frequency, it means that the blue light has more energy. I'm going to just briefly talk through the mark scheme of this as well. So one of the points, it gives 2 extra points, but you can only get maximum 4 marks. And it mentions the Einstein's photoelectric effect equation. And it says just simply by stating the equation and what each symbol means, you get the mark for it. Another point could go to stating that a wave model will not explain instantaneous emission. And in the guidance, it clearly says to score full marks, the answer must include 2 terms out of photon, work function, and threshold frequency or wavelength. And that's a very important part to keep in mind. You will not get full terms if key terms are not used, full marks if key terms are not used. So let's go to part C. It says the longest wavelength of light incident on the metal surface, which causes electrons to be emitted, is 480 nanometers. So right now I know that this is the maximum wavelength, which means for this wavelength we'll be able to calculate also the minimum frequency. Remember, they're inversely proportional since the speed of light remains constant. It says show that the work function of the metal is about this much. Now work function, straight away I should know it's simple phi. As soon as I see these terms, I should be labeling them. It's a good habit to get used to. That way when you look at the formula booklet, you're not wondering, oh my god, which equation am I going to use? At least when you look at it, you'll be like, oh, I know what phi is, I know what this is, I know what that is. And looking at this number is in joules, so what is that? That's energy. Now once again, work function is one of the key terms that you need to be able to define. It is the minimum energy needed to remove an electron from the surface of a metal. So we know that just to remove it, not to give it extra kinetic energy. And we already know that HF, so the energy of a photon, is equal to the minimum energy required to remove it plus any extra kinetic energy that's left for the photon after the photon gives enough energy to the electron to escape. But since we only want to show the work function, I'm assuming that my photon, and in this case, since this is the maximum wavelength, which means the minimum frequency, then if kinetic energy is 0, so just about 0 joules, so just about when my electron is removed from the metal but has no extra kinetic energy. So the minimum energy can be found using HF naught, whichever naught is already mentioned here. But since I'm given the wavelength, instead of having to do all the calculations and everything, I will use this equation, rearrange and substitute in. think the formula booklet gives it to you straight away. It's your choice, whichever way you do it. And then you just put the values in. So 6.63. It is found at the formula booklet at the back. Please make sure you're familiar with it. And divide the whole thing by 480 nanometers. Now, a lot of you keep trying to divide by, or to multiply by unit prefixes. Only multiply what the unit prefix is. So nano is times 10 to the minus 9. So just simply do times 10 to the minus 9. And then the unit is meters, so you don't really care about that after that. And when you put it all in a calculator, you should get about 4.14 times 10 to the minus 19 joules. You should usually, when you are told to show, because you have to show that the answer is that, you have to give the answer to more significant figures than the answer that's shown to you, and then you should say approximately 4 times 10 to the minus 19 joules. There are questions that could ask you to give this in electron volts. If I wanted to, even though this question is not asking that, I'm just going to quickly talk through it. We know that 1 electron volt, we know that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So how many electron volts would 4 times 10 to the minus 19 joules be? So you just simply divide the number of joules you have by what 1 electron volt is in joules. So it will be 4 times 10 to the minus 19 divided by 1.6 times 10 to the minus 19 to give you that. I usually use the method of 3, so you cross them. You have to have the same quantity on both on this side, the same quantity on that side. And you multiply the two numbers that are known, and you divide them by the one that's with the unknown number. That's just an easy ratio way of looking at it, and then that should give you an answer for in terms of electron volts. In this case, it would be roughly 2.5 electron volts. Even though the question did not ask us to do that, I still did it. Just to remind you that electron volts are an important part of this topic and how to convert between them. Now, the next part says calculate the maximum speed. It's very important. Vmax, this is what I need to find, of an emitted electron. So we know that when electrons are emitted, they're moving. So if they're moving, they have kinetic energy. That's one of the important parts. So they have kinetic energy. We know kinetic energy is also linked to the speed of the electrons. So that's another good thing to note down. So calculate the maximum speed of an emitted electron when a photon of energy 5.2 times 10 to the minus 19 joules is incident on the surface of the metal. So I know that this is my HF, this is my photon's energy. Now, we already have seen another equation. You might think like, oh, how am I going to find the speed? We didn't learn that. This is when application comes in. So you know that the energy of a photon is equal to the work function of the metal plus the maximum kinetic energy. These are all the terms already that we have seen. Now, this question is asking you about speed, which I linked directly to kinetic energy. So that's one of the terms that you see here. We know the energy of the photon is HF. And we also, in the previous part, since this is part 2, remember not to forget that we have previous parts giving us other values. So we calculated other values in the previous parts. So in this case, you could use your work function that you got here because it's the same metal. So it's 4.1. Let's just leave it as 4.1. So phi is 4.1 times 10 to the minus 19 joules. And you can notice here, I'm not using electron volts because all of the values have to be in joules. When we use values in equations, they have to be in joules unless all of them are in electron volts, and that's fine. I'll explain that if we come across another question that involves that. So I don't need to calculate the energy of the photon because it's given to me already in joules. Before I proceed, since I want to calculate the speed, I will make sure I rearrange to make the kinetic energy the subject of the formula, since that's what I need to work through. So kinetic energy max is equal to hf minus phi. Hf, once again, being the energy of the photon, phi being the work function, the minimum energy required to remove it, and then the rest of the energy remaining from the photon that was given to the electron is used to speed away from it. So we can calculate kinetic energy maximum in this way. First, if you would like, or we can keep the numbers in the equation, the symbols, and then put the numbers in. Kinetic energy, we said, is a half mv squared, which is equal to hf minus phi. Now I'm showing all of my steps, to make sure that I do achieve all of the marks. And then I just simply rearrange. I have mv squared is equal to 2 times hf minus phi, and v squared is 2 over m hf minus phi, and then I square root it. You can simply leave it like that and then put the numbers in, like I said, or you could put the numbers in here, so you could do the subtraction directly. It will be 5.2 minus 4.1 times 10 to the minus 19, and then you can use that directly, or you can just simply leave the numbers to be put in last in the equation, so you don't have to put too many numbers in the calculator. Just keep it to one equation only. I don't have a screen for the calculator to show you this, but I will figure that out as I go. So yeah, you should get a number. Now, obviously, m here being the mass of what I'm measuring. So this is the kinetic energy of the electron. So I know the mass of an electron. Every time you see an electron, you know its mass and you know its charge. They're given to you in the formula booklet. So electrons are, a big hint in terms of what its mass is. So this is the mass of the electron here, which is 9.1 times 10 to the minus 31 kilograms. Just put the numbers in and you should be getting 4.9 times 10 to the 5 meters per second, which is logical since it's not faster than the speed of light, and since it's removed from the metal surface, it shouldn't be much faster than that. So it's a good logical number. Describe briefly one piece of evidence. So I need to describe, not explain, just describe a piece of evidence for believing that electrons sometimes behave like waves. This is talking about the wave-particle duality of electrons, and we know the experiment for that is simply passing electrons through a polycrystalline, so electrons fired through polycrystalline graphite. So since it's 2 marks, remember that, yeah? Since it's 2 marks, then I need to also include what happens to it when it passes through it. So it passes through it, then it produces diffraction rings on the screen. It's usually fluorescent screen. I will go a little bit more into it later on if we have enough time, or because we will have to come across how that screen works eventually, but I'll focus on it in another time. Now it says calculate the Debroglie wavelength of an electron moving at 500. Oh, I think I should use a highlighter for this. So here I'm. This is what I need to calculate. And this is what I'm given. So the electron is moving. I know that I have an electron, so I know its mass. I know the mass of an electron. I know its charge already as well. And I know its speed. Now, the speed is in kilometers per second. I want it to be in meters per second, otherwise it won't work with my equation. It will give me wrong values. That's 500 kilometers per 1 second. But I want it to be meters per second. Kilometers is times 10. Kilo is times 10 to the power of 3. So I have 500 times 10 to the power of 3 meters per second. So there it is. Fixed that already. The Debroglie wavelength we know is given through this expression. However, we know that P stands for momentum. Lowercase p is for momentum. This is lowercase p. So h is mv. We know that momentum is mass times velocity. We know Planck's constant. It's given to us in the formula booklet. Mass of an electron is also given to us in the formula booklet. And the velocity of the electron that is moving in meters per second is this. So then once I put the numbers in, I will get 1.5 times 10 to the minus 9 meters. A quick hint here is if you can't be bothered to put all the numbers in, or if you want to save time putting the numbers in and you're really good with your indices and know how to work them, then you can focus on the powers just to simplify them to just one power. So this is 10 to the minus 34. Since this is a denominator, when you bring it up, it's going to become positive. Times 10 to the minus 3, this becomes negative. And you end up having minus 34 plus 31 as minus 3. And minus 3 plus minus 3 is minus 6. So you could replace that all with just simply power. Simply by this power. I'm not saying this to confuse you. If you find it that this works better, then that's great. If you want to start simplifying your powers and putting less in your calculator, then you can just use your indices laws and make sure you don't get confused with it. So looking at the second question, this is in a demonstration experiment of photoelectric effects. So once again, it's talking about the photoelectric effect, light of wavelength. So we are given a value there, label it ahead, because obviously you will need to use that number somewhere. Incident on a clean metal surface causes electrons to be emitted. No electrons are emitted from the surface when the wavelength of incident light is greater than 550 nanometers. So that's another value that you're given. But this is the maximum wavelength, which means it was linked to the minimum frequency. Remember again, frequency times wavelength. So if that's the maximum wavelength that we can have, that means that it will be, the frequency will be the equivalent of the minimum frequency. Now it says define, so this is an easy one. Define work function. However, it is 2 marks, so that means that you need key parts of this question. Now, the work function is the minimum energy. That's 1 mark for stating that it is the minimum energy for an electron to escape from the surface of a metal. Now, if you don't mention this part, you will not get the second mark either. If you just set minimum energy for an electron to escape, that will give you 1 mark. Sometimes these questions could be only 1 mark to begin with, and you will need to include both key underlying parts to it. But the fact is that you can't remove a work function is not a definition for an electron to escape from any surface. It has to be from the surface of a metal, so it can't be from an insulator or anything else. The next question says, explain how the work function is related to the threshold frequency. Once again, the key words, the key definitions. So we need to explain how they're related to each other. So a photon, we need to mention photons because that's what it is linked to. So a photon with a frequency below the threshold frequency cannot cause electron emission. Therefore, work function is equal to HF naught. Now here you need to make sure that you label what each one is. So threshold frequency is the F naught, H being Planck's constant, and phi being the work function. Make sure that they're all clearly labeled, otherwise you will not get the mark. So that's 1 mark for stating what threshold frequency kind of is and how it's related to the equation. Now it says calculate. So obviously you need to show calculations, you need to use the right equation, the value of the work function of this metal. Now going back to the values given at the top, because obviously there's no values given in this part, but they're all given here. You are told that you have a light of that wavelength being emitted, but no electrons are emitted when the wavelength is above this value. And I've already said, since it's as the maximum wavelength, then that means that the frequency will be minimum at that point. We know that the energy of a photon can be calculated with this, so that's the minimum energy that will be required by a photon to remove an electron from the metal, and that's equal to the work function. So we just simply put in the numbers. Once again, remember the nanometers. You can simplify, like I said, the indices. So 550 times 10 to the minus 9. And you should get a value of 3.6 minus 19. And that looks quite logical. It's we do expect to the minus 19, 18 joules worth of energy. Then the next part says show that the maximum speed of the emitted electrons in the experiment is about 4.5 times 10 to the 5 meters. Since we're showing it again, remember we talked about this. This is quite similar to the previous question we have seen. So we have the work function is equal, the energy of a photon equal to the work function plus the kinetic energy max. We already calculated the work function in the previous question, but we also know that the wavelength is this wavelength, the 440 nanometers wavelength that we need. And hence we can just simply place the numbers in now, and instead of using HF, I'll use HC over lambda. I'll just rearrange. Kinetic energy max is equal to HF minus phi. In this case, it's HC over lambda minus phi. You can do the calculation straight away, so you can put the numbers and get whatever value you get there. 440 times 10 to the minus 9. Remember always to convert your unit prefixes, as very important. You can label it just as you're reading it so you don't forget. That makes it a bit more obvious. So whatever number we get there. So I forgot to add all of the values there, so I just added them now. So this will give me this answer. This is equal to kinetic energy max, and that's equal to half mv squared. So remember, kinetic energy has its own equation. We rearrange. V is equal to 2 times 9.2 times 10 to the minus 20 divided by the mass of the electrons, because I'm dividing both sides by the mass, which is the mass of the electron, and then you square root to find the answer, which will give you 4.45 times 10 to the 5 meters per second, which is approximately 4.5 times 10 to the 5 meters per second, as required to show. I'm going to go to the next part BII. It says calculate the minimum Debroglie wavelength. I know already that L is equal to H over P of an emitted electron. In the previous part, we calculate the maximum speed. Now, to remind you, wavelength is equal to the momentum, is inversely proportional to momentum, and momentum is mass times velocity. So if this is the maximum velocity that we use, that calculated in the previous part, so the biggest denominator will give me the smallest wavelength. So I will use the speed from the previous part. I know the mass of an electron already. So wavelength is Planck's constant divided by the mass, which is 9.1 times 10 to the minus 31, times the maximum velocity that we we found in the previous part, and that should give us 1.6 times 10 to the minus 9. So quite a small wavelength. And you can see that electrons have a very tiny wavelength, so it's actually of the order to the minus 10. That's the size of atoms. That's why electrons actually get diffracted by two carbon, the spacing between two carbon atoms in graphite, because this gap is the gap between two atoms, which each atom has a diameter of 10 to the minus 10. So the spacing between them is roughly like that. Since the gap is similar to the wavelength of an electron, it diffracts. So the light source of this experiment, okay, so this question has to do with energy levels. You have not covered that yet. You have seen them in your GCSEs, but we will also come across them again in chapter 19, which shows you this is a synoptic type of question for AS and A2 years. I won't go through it now, but we will come across it when we do work on stars and how we use the concept of photons and electrons, moving from one shell to another, from one electron level to another later on. So I will be skipping this part. Don't worry about it. Delete it from your total marks as well, so you don't feel like you're being unfairly marked. Now this question 3 is about electrons and photons. Both electrons and photons can be considered as particles. State two differences between their properties. So here we are trying to compare electrons and photons' properties. When we talk about properties, meaning their charge, speeds, mass, and so on. So in this case, electrons have mass and they have charge, negative charge, whereas photons are considered to have no mass and they are uncharged. That's enough. You could have said that photons travel at speed of light, whereas the electrons are a bit slower than that. An electron is accelerated, so part B now, an electron is accelerated from rest through a potential difference. So I know V is that much. Show that the energy gained by the electron is this much. So once again, I'm showing, I need to do calculations to show that. Instead of saying calculate, it says show that that's much, meaning that you have to calculate it. We know that when we have a potential difference that accelerates an electron, it causes the electron to gain energy. So it goes from rest to a specific speed based on how much potential difference we're giving. And we know that that energy transfer, that energy gained by the electron can be found using this equation, VQ. Remember, the potential difference is work done per unit charge, or the energy transferred per unit charge. This means energy transferred or work done. And we know that the charge is the charge of an electron, because it's the electron gaining that, only one electron gaining that energy. So we have the charge of an electron times the potential difference. This is again a reminder of the electron gun. We have seen this before, which shows you how widely it is used. So please make sure that you are used to it. And that should give you something quite small. So 8 times 0 times 10 to the minus 16 joules. So we showed exactly what they asked. Show again that the speed of the electron is about this much. We know that since the electron went from being at rest to moving, it's gained kinetic energy. So the energy gained through the potential difference has been transferred in terms of the kinetic energy of the electron. So the work done now, the kinetic is the kinetic energy, which is equal to half mv squared. Since it's the second part, we already calculated the work done here. So if you couldn't even show this part, you will be able to show, you should be able to show this and gain the 3 marks from there. So you need to simply rearrange the values that you have. So 8 times 10 to the minus 16. I times both sides by 2 to get rid of 2 from here. So 2 divided by 2 is 1. So we have 2 times 8 times 10 to the minus 16 is equal to mv squared. Now I need to get rid of m, so I divide both sides. I'll do it like this. Divide both sides by m. M divided by m is 1. It's like 5 divided by 5. And that's the mass of the electrons. Still, we're focused on electrons. So v squared is 2 times 8 times 10 to the minus 16 divided by 9.1 is 31. And then the reverse action of v squared is to square root both sides. So I'm going to square root both sides. Square root and squared cancels because it's like saying v squared times a half. So 2 times a half is 1, so that's v to the power of 1. And that's what this means. And therefore we have this. And then you should get the value that's given to you in the question, which is roughly 4.2 times 10 to the 7 meters per second, which is roughly 4. Explain what is meant by the Debroglie wavelength of an electron. In this case, it might look hard what it's asking, like what would it really actually want us to say here? You just basically talk about the direct relationship between the wavelength and the properties of the electrons. So in this case, it means that the electron wavelength depends on the speed or momentum of the electron. That's the only relationship we know in terms of Debroglie and the features of an electron. It says calculate the Debroglie wavelength of the electrons. So once again, it's quite straightforward. You constantly have the same equation. You have the mass of an electron. You already calculated, and you were even given the speed at that point. So you, even if you didn't answer these two parts, you could still go on to gain 3 marks from here. So you place all the values in, and you should get 1.7 times 10 to the minus 11 meters. So extremely tiny wavelength. The faster an electron moves, if you look at the previous questions as well that we looked at speeds of electrons, they were to the power of 5, which gave us a larger wavelength. In this case, the faster it moves, the shorter the wavelength it has. And part D is asking you to calculate the wavelength of a photon of energy 8 times 10 to the minus 16 joules. So that's the energy a photon will have. We know that energy is equal to hc over wavelength. I need to rearrange to make the wavelength the subject of the formula. So it's going to be wavelength equal to hc over E. It's like switching the positions, but if you want to do it step by step, you times both sides by wavelength. Wavelength divided by wavelength is 1. So you have wavelength times energy is equal to Planck's constant times speed of light. And then I want to lambda on its own, so I'll divide both sides by E. That's 1, so then wavelength is hc over E. You can use numbers as well to confirm that if you feel like insecure about it. So just use simple numbers, 1, 2, 5. They're good enough. So then we have the wavelength. Put the values in. So long to keep writing this, but it's good for the practice, quicker. That's why I say usually try and minimize your numbers that you have to put in your calculator in order to save time if you're confident with it. So the wavelength will be 2.5 times 10 to the minus 10 meters. It says photons of that energy, so now it's giving me a different number, are incident on a clean tungsten surface causing electrons to be emitted. State the name of this process. So what causes electrons to be emitted? What is the process called when photons are emitted from the metal surface? That's what it's asking me. Okay, I'm going back reading and thinking, okay, what process is it talking about? We have electrons being emitted from a surface metal due to photons. That is the photoelectric effect. So we have photons removing electrons. So photons removing electrons from a surface of a metal. Calculate the maximum kinetic energy of the emitted electrons. So Ke max. And it tells you the work function of the metal, and then here it gives you the basically HF of it. So this is quite a simple one. You have HF is equal to 5 plus kinetic energy max, which means that you just rearrange. So HF minus 5. Just put the numbers in, and you have 9 minus 7.2 times 10 to the minus 19, and that should give you 1.8. Now these are simple questions. I haven't seen something extremely hard, but I will be doing more videos as your requests, and I will also include some exam questions from 2016 in this video. So explain why your answer to I is a maximum value. Why is the kinetic energy? So you need to explain why that was a kinetic energy max and not just kinetic energy minimum. So if you remember from the video regarding the content that you need to know, I have a metal piece, have the ions, well, the nucleus that are fixed, positive ions are fixed. Then we have a lot of electrons, delocalized electrons everywhere. Now, electrons that are closer to the positive charge are attracted much strongly, so they will require more energies. So, in other words, electrons in the metal require a range of energies in order to be removed. That means that most of them will require more than the work function to escape. Which means they will have less energy from the photon as kinetic energy. So I'm saying that if I'm giving this much energy to all of my electrons, if they have a bigger energy, if they need more energy than the work function, so that the minimum energy to be removed, so this will need the least amount of energy, whereas this will need more energy, and then this will need even more energy, so that will be a bigger number. Then that means there will be left. So the bigger the energy that they require, the less the work function, the less the kinetic energy they will have at the end. So you could explain it in those terms as well. You do need to be clear about what you are talking through this. If you use the equation, label it. If that's the minimum, you can use numbers to show it as well. That's pretty much the whole paper. I will go through some other questions now as well, that are from the actual OCR paper in 2016. This is the breadth paper of 2016, so the new specification exam questions. In the breadth paper, there's not too many questions on quantum, on this breadth paper anyway, but in general it varies per year. The first question that I came across is number 4 in terms of quantum physics. I will go through these papers in detail as well later on. It says electrons traveling through a thin film of carbon are diffracted. Which statement is correct? The fact that the question says that they are diffracted is a very important part, and we know that this is proof of wave-particle duality of electrons. Then it says to correct which statement is the correct statement, not incorrect. Okay, that's very important. So the electrons behave like photons and are deflected. Now, deflected means it doesn't even touch it, it deflects from a positive charge or something, or negative charge, so that's not true. Photons, the electrons behave like photons and change direction as their speed changes. That's not true, their speed actually does not change. Waves are refracted by the holes into in the carbon film. That's not true. They don't refract. They don't change direction and speed. So that's what refraction does, changes direction and speed. And waves, the electrons behave like waves, which this is what wave-particle duality is, of wavelengths similar to the spacing between carbon atoms. Excellent. That's the main thing to take from the whole setup for that. Now the next question I found was question 15. This is a little bit hard, and remember these are 1 mark worth, so you need to be extremely quick and careful with them. These type of questions are quite common, especially when it comes to a before and an after situation. So it says the electron gun is used, and we know about electron guns. We've seen them in chapter 8 or 9, if I'm not wrong. We know, and we've already seen them in a previous question as well. It says an electron gun is used to accelerate electrons from rest through a voltage V. The electrons emerge with a speed U. Once again, we know that the voltage here provides energy for the electrons to accelerate from rest. So they're not moving initially, so kinetic energy is 0 initially, but then they end up emerging with a speed of U, which means that the kinetic energy is a half mu squared. We know that the energy is based on V, so work done and energy transferred is QV. Since electrons are being accelerated, then the charge of an electron is elementary charge. So we know EV is equal to half U squared. But then it says the voltage in the gun is halved. So this voltage halves now. So this is the original expression. Now we need to make sure that this expression remains when we add our fractions in there. So now the voltage is halved, which means if I write it in a nicer way, it will be like this on this side. And also, how will this affect the velocity now? I know that I can't affect a constant number. I can't change half. I can't change the mass of an electron either. It is fixed. So these two numbers remain constant, but that means that this will have an effect on the speed. So there needs to be something in front of the speed here to take into account that I halved the voltage. And in this case, it will be 1 over square root of 2 U squared. Now I can double check that this is the fraction at which it changes by expanding my brackets. So that's going to be a half EV is equal to a half 1 over square root of 2 will result in a half, and that's U squared. So if I do that all together, is a half times a half U squared. So once again, if I remove this factor that I half the voltage with, I end up back again to where I began. So this is me double checking. This is a double checking part. But by doing this, I figured out that it's C, so that's the correct one. Then we have question 16. It gives me the energy of photons that are incident on the surface of a clean metal plate. It gives me the work function, which is phi, and it's asking me to find the maximum speed of the emitted electrons. Remember, kinetic energy, once again, is linked to speed of any object, and since we're given energies, we know that we can go from the kinetic energy to the speed through that way. So we have HF is equal to phi plus kinetic energy max. We do the same rearranging again. I'm just going to write it straight away because you have already seen me do that quite a bit. So then V will be 2 over HF minus phi. As I said, you don't have to do this all at once. If you want to do the subtraction first and then put the number in there and rearrange, that's totally fine. It's just for simplicity, I tend to use this. So your expected answer should be A. Once you put the numbers in, it will be square root of 2 over, since it's electron again emitted from the surface, it will be 9.1 times 10 to minus 31. And then you just subtract the energies, 4.8 minus 3.2 times 10 to the minus 19. Just put the numbers in and you should get A as the correct answer. And the next part that I only found in the written part in the 2016 Bird paper was part C, the very last question of the paper, but it is a very important question in terms of how we see things in units and rates. So in this question, it tells us the wavelength of light from an LED. Before I continue, this question involves electricity topics and more precisely LEDs. So it starts off with a question on LEDs, the characteristic of an LED, what is going on in terms of resistance and current and potential difference at the different regions of the graph. And then it goes on to ask you questions about what's wrong with the circuit, why is it not working, how can it be investigated, and then it links it directly to quantum physics, which we have seen LEDs and how to use them to get Planck's constant, but in this case it's not asking us to find Planck's constant, it's asking us to do different things. So the wavelength of light from the LED is this much. So like I said, always label your unit prefixes if you forget to put them in the equations later. So the radiant power emitted from the LED is 1.2 milliwatts. So that's times 10 to the minus 3 watts. Calculate the number of photons N emitted from the LED per second. Now power is equal to the energy per unit time, so the rate of energy transmitted. I'm given the wavelength of light from the LED. So I know light is either a wave, or it can be seen as a wave, or as a packet of energy, a photon. So if I want to know how many photons are emitted from the LED, I have to figure out the energy of one photon to begin with. So the energy of one photon is hc over wavelength, which is 6.63 times 10 to the minus 34. This is so long to keep doing, but it's worth it. And you should get an energy of about 4.1 times 10 to the minus 19 joules. So this is the energy of one photon. However, the power emitted by the LED is 1.2 times 10 to the minus 3 watts. So energy is linked to this, to power as the rate of energy transferred. And since I know the energy of one photon, I know the energy, actually in this case, let me rename it. So I know that the LED is emitting a power, or is emitting 1.2 times 10 to the minus 3 joules worth of energy every second. This is exactly what this means. This is what power means. So per second, 1.2 times 10 to the minus 3 joules of energy being transferred every second. But each photon has this much amount of energy. So how many photons are involved? Where the number of photons, we said each packet of energy has this much energy. Each packet of photon has this much energy. So how many photons can give you this much energy? So 1.2 times 10 to the minus 3 joules is how many photons if one photon. You can see that's a ratio. This is an application question. Even if you didn't come across this question before, you are expected to be able to answer it. But usually ratios like this repeat constantly, and the more practice you get, the more confident you will feel. So how many photons? You can use the method of 3, or you can do it as a ratio. So that will be 1.2 times 10 to the minus 3 joules divided by 4.1 times 10 to the minus 19 joules, because it's asking me how many photons are emitted per second. So if each second this is how much energy is given, then I know how many photons are emitted every second, and that should give me a value of 2.9 times 10 to the 50 photons per second. Very important to make sure that we understand each part of the question. Now we link the power to energy. You should be seeing power as that. is the rate of energy transfer. So if the power is 60 watts, it means 60 joules of energy are being transferred in 1 second. Don't let the indices, the powers of 10 put you off. I'm going to also go through the depth paper and see what questions we can get from there. Now this is a question from the depth paper in 2016. It includes more questions on quantum physics. The first one is a 6 marker, which is a really good opportunity for us to have a look at 6 markers. In this question, it shows you the gold leaf electroscope, tells you that it's used to demonstrate the photoelectric effect. Straight away from there, you should include something about what the photoelectric effect is, and you should know that already from the definitions. It says a zinc plate is placed on top of the electroscope. The zinc plate is negatively charged. White light from the table lamp is allowed to fall on the electroscope from a distance of 10 centimeters. So this is what's shown here. It tells you that you have light 10 centimeters away from the zinc plate, and the gold leaf takes a very long time to fall. But then the experiment is repeated with light from a distance of 4 centimeters. In this case, again, same result. They're waiting for a very long time for the gold leaf to fall. Remember the repulsion between the gold leaf and the metal stem, because they have the same charge. So there's a lot of electrons built up around there. And then it says both experiments are repeated with UV radiation. So then we have UV at 10 centimeters and UV at 4 centimeters. And it tells you what happens at each case. So in this case, in the 10 centimeters, the gold leaf falls quickly. And then at 4 centimeters, so even closer to it, it falls much quicker. So then this question goes on to ask clearly what it wants is explain how these observations demonstrate the photoelectric effect. So I need to focus on the photo, explaining how it is linked to the photoelectric effect, and provide evidence for the particular nature of electromagnetic radiation. So this is the second point. So I need to state how these observations, I need to explain how these observations are evidence that EM radiation behaves as a particle, so particulate, particle nature. So to begin with, we need to plan a bit. I will use some of the space here to plan below it. So have 2 things to answer. One is how the observations demonstrated. The second one is how it provides evidence. So for the explanation, we could talk about the fact that light is shown, no electrons are emitted. So there is no effect, no photoelectric effect, basically, with light. The only reason that it discharges after, so the gold leaf takes very long time to fall, basically, is because it naturally discharges over a long period of time. If this experiment was done in vacuum, there would be no other particles in the air to affect it, so it would stay like that forever. But since it's done in normal room conditions, well, it doesn't say it, but we're assuming it is, then you have ions in the air, so charged atoms that could have enough energy to absorb the electrons from it and hence attract the electrons from the surface of the metal. So the natural discharge, naturally discharge So I know that that's the reason why having light at 10 centimeters or light at 4 centimeters gives me the same observation. It's because light does not cause photoelectric effect. And the only reason that it naturally discharges, naturally the gold leaf falls down, is because of the electrons naturally discharging over time. Also, you can mention here that since you have UV radiation has higher energy. Or UV photons have high energy, so they do discharge by emitting photons. So they emit UV emits photons, photoelectrons, sorry. It also constitutes an instantaneous emission or discharge, which is very important because it says the gold leaf falls quickly at 10 centimeters, but at 4 centimeters, UV is more intense, but it results in a faster rate of emission. So this means that UV photons that have higher energy emit photoelectrons at an instant. When it's closer, the UV is more intense. This results in more photoelectrons being emitted because you have more photons with enough energy to remove them. And there is no effect of changing the intensity. So the distance in this case is linked to intensity. It's like having a flashlight. So if you have a flashlight that's further away, it will have the light spread over a bigger area, so you have less intensity. But if you focus on a smaller level, so you have the flashlight here, it will have more intensity, so the light will be spread over a smaller area, so more intense. But it appears that the distance does not, the intensity of white light, so light intensity has no effect. So now we need to think about what can I include as evidence that link to EM waves being seen as particles, as photons. So to begin with, we could talk about that the wave theory expects that the leaf should fall at any intensity from light. But we see as packet of energy, but seeing it as a particle, as a packet of energy. So we see photons as packets of energy in a 1-to-1 interaction. So the energy of a photon is directly proportional to its frequency, and we also know the equation that you can state it and explain it. So the energy of a photon is given to the electrons who have a minimum amount of energy that requires to be removed, and then they have the rest of the energy. So this conservation of energy, in other words. If you're going to use symbols, please do define each symbol in your question, even if it means you write it on the side as a scale. It's very important. Otherwise, you might risk losing the marks. So in this case, to explain it, I did add a bit of an explanation here, which should have been in this side. But I will go on to it now. So you could go on to say that UV photons have a frequency above threshold frequency. F naught, remember F naught is the threshold frequency. That means that light photons have less energy than the work function. And you can go on to also mention that intensity is not linked to energy, like waves. So these are the key explanations involved behind why we see what we see. So we are stating the observations and we're explaining them. You can notice here that it's asking about the intensity. So the distance in this case was the trick. So the fact that you have something closer and further away is linked to the intensity. This was the link that you had to make here. And you had to talk about how different EM radiate different frequencies. So EM frequency, how it affects. So you have light and UV, which both have different frequencies, and you're also comparing the intensities. So EM intensity. Here it doesn't ask you anything about the kinetic energy and how that's affected, so you do not have to talk about it here. Otherwise you will waste extra time that you could be answering important questions. This is part B of this question. It says in another experiment, electromagnetic radiation of frequency. So here it gives us the frequency of the photon, for example, falls on a negatively charged metal surface with a work function of 3.2 electron volts. This is what I meant by giving you different values in different units, and you will have to end up converting. So that's my 5-value work function. Calculate the maximum kinetic energy in joules. You need this in joules, it's very important. So this is what I need to calculate. To begin with, I need to make sure that I know what I'm doing. So I have the incident photons, which have this frequency. So HF, I can find the energy of a photon, which is equal to the work function plus the kinetic energy max, or EK if you want to label it in that way. So I will rearrange, make kinetic energy the subject of the formula, and then I will start substituting my values, into the equation. Here I have 6.63 times 10 to the minus 34 times the frequency, which is 9.60 times 10 to the 14, minus the work function. Now the work function is given to me in electron volts. It says 3.2 electron volts. How much would that be in joules if 1 electron volt is 1.6 times 10 to the minus 19 joules? It's a simple ratio. If you are not used to the ratios and you're finding it a bit too much, this is a simple way of thinking about it until you get used to it. Do it more and more often until you feel more confident with it. So then that's minus my work function, which is 3.2 times 1.6 times 10 to the minus 19. And that should give me my value, which is 1.2 times 10 to the minus 19 joules. Question 8 of, once again, the depth paper of 2016 has to do with the electron diffraction. So already as soon as you see that, you should be aware of the wave particle duality. It says it provides evidence for the wave-like behavior of particles. Electrons are diffracted by a thin slice of graphite. In one experiment, electrons are accelerated from rest through a potential difference of 300 volts, so that the final speed of electrons is 1 times 10 to the 7 meters per second. When once again, here is a reminder of the electron gun application, and even we saw questions like this in quantum physics. We know that energy gained by the electron can be found using this equation, and since the energy gained is being used as kinetic energy, so the electron is moving fast, then that energy is equal to the kinetic energy. Using this equation and rearranging for V, you get 2 EV over m square root. So what I did, I multiplied both sides by 2, I divided both sides by m, and then I square rooted both sides. Determine the Debroglie, I forgot to even show the number. So we have square root of 2 times the charge of an electron times the voltage divided by the mass of an electron, which should give you 1.03 times 10 to the 7 meters per second. But since we need to show roughly, it's 1.0 times 10 to the 7. So if you need to show something, calculate basically something, you always calculate it to an extra significant figure, so you can show that it rounds up or down to that. Moving on to the next part, determine the Debroglie wavelength of electrons. We know that this is the equation for it. So then we have 6.63 times the speed that we calculated above. And that should give us about 7.3 times 10 to the minus 11 meters. It's the last part. It says after the electrons are diffracted by the graphite, they hit a fluorescent screen. The electrons are diffracted because of the spacing between the carbon atoms is comparable with the Debroglie wavelength of the electrons. Figure 8 shows the diffraction pattern, bright rings seen on the fluorescent screen when the electrons are accelerated through a potential difference of 300 volts. So it basically told us what we already know. And it says the potential difference is now increased. So V now increases. Explain how the diffraction pattern will change. So when we see a pattern, we see these really bright rings. He's calling it bright rings here, the diffraction pattern. How will that be different if I increase the potential difference? And that's 2 marks. Before I start answering this question, I want to remind you that we calculated the energy of the speed of electrons using this equation. So the voltage is directly proportional to speed squared. So if I increase the potential difference, the speed of electrons increases. And I already know that wavelength of the electrons is inversely proportional to the speed. So if the speed increases, then wavelength decreases. So this is 1 mark, which means that the radius of the rings or the diameter of the rings decreases as smaller wavelengths tend to diffract less than bigger wavelengths. I hope this helps. And any questions you have, please let me know regarding all the work I have set for you. Any videos you want me to make on any specific questions, please also let me know.